Okay, I think everyone's familiar with Newton's third law of motion if they're watching this video. If you exert, for every action, there is an equal and opposite reaction. So if you push on a box, the box pushes on you. And I kind of don't like the terms action and reaction, mainly because reaction makes it sound as one force happens at a certain time and then the other force happens at another, and that's not the case. They are simultaneous. And another reason why I don't like the term is because it makes it sound as if they're quite separate from each other, but this is an interaction between two objects. So you can think of it as any interaction that goes on between two objects is going to have a pair of forces that are equal in magnitude. So, pair of forces that are equal in magnitude and opposite in direction. And so it doesn't matter how many objects in the system, if they're interacting, every pair of objects that's interacting should have a pair of forces as well. And so I like you to get to thinking of it as an interaction between the two objects rather than like a sequence of events. One common misconception that I see all the time with third law, imagine, if you will, a table. And perhaps I have placed a apple on it, or I don't know. That's not appleish. Anyway, let's make it a box. So place a box on the table. The free body diagram for the box, I would have gravity pulling down. I would have normal pushing up. And some people say, oh, well, the normal force is equal and opposite to the weight, and say that's the third law pair. But remember, the pair is between the objects. So if I rewrite this, this would be the force of the earth on the block, and this would be the force of the table on the block. So these can't possibly be a third law pair because we have three objects involved. Another reason that they can't be a third law pair, they're on the same object. The other pair, each of these has a reaction to it that has to be on another object. So if I draw this for the table, that was terrible, but oh well. It would have gravity pulling down, so force of earth on table, and normal force from the earth, force of earth on table, and we would have the box pushing down on it as well, so force of box on table. Notice the normal force from the earth and the gravitational force from the earth, they're acting on the same object, and even though there's only two objects involved, the fact that they're acting on the same objects is enough to tell us they are not the third law paired to each other. Another way to tell, in both cases, we're comparing a normal force to a gravitational force. The third law pair is always going to be the same type of force. So in this case, the force of the book on the table should be the third law pair to the force of the table on the book. We would see the gravitational third law pairs from the earth. So if the earth pulls on the book is going to pull on the earth. And if the earth pulls on the table will pull on the earth. It's just when we see objects that are pulled on by the earth, they fall to the earth, and we don't really see the earth falling to the other object. That comes back to first law and second law. The earth has so much mass, it has so much inertia, it's going to experience a tiny little acceleration compared to the falling book or table or whatever is falling Did I change box to book? Okay, well, anyway, so the G is going to be much greater than whatever the acceleration the Earth would experience, and that's all due to it having a massive mass. So, third law, the two forces must be equal. So, if the Earth is pulling on the tiny little book, massive Earth, light book, we're going to have a light acceleration, big acceleration. And so that's what determines what moves, not the force, because the force is always the same on the two objects. It's the inertia of each object. Before I go, I want to go into how I solve third law problems. So let me give you an example here. Let's say that I have a stack of boxes. So we'll say M, and we'll say M over 2. And let's say I want to find the force of the bottom box on the middle. Well, we can draw a free body diagram for each box, but that kind of gets complicated. Instead, what I want you to do is find out where that force should be located, and that's where you break the system of objects into two. So if I want the force between the bottom and the middle, I'm going to break the system right here into two separate systems. So we'll have a free body diagram for the bottom box and a free body diagram for the top two. So here we would have gravity pulling down, normal force from the floor, and then we would also have the force of the middle box on the bottom. Notice that is the third law pair to the force we're looking for. So we could solve for this one and just know that it's going to be upward. But we don't know what the normal force from the floor is. Remember, it's going to change to try and match the two downward forces together. So this isn't really helpful. But we went ahead and broke the top portion away from the bottom. And we're going to see why. I'm going to have gravity acting on the system of the two boxes. So M plus M over 2 times G. And we don't have the normal force from the floor acting on them. It's acting on the bottom box. Instead, we have the force of the bottom on the middle. This is the force we are looking for. And this is the only other force involved. So if these boxes are just at rest, we can say the force of the bottom on the middle is M plus M over 2 G. We could take it one step further and solve for the normal force. We know that this has to be equal to the middle on the bottom as well, just opposite direction. So our normal force should be equal to mg plus m over 2 g, which this is really just the entire mass of our system times g, or rather we can think of it as the weight of the system is equal to our normal force. And that's how you solve third law pairs. Break it where the force is located, that the force that you're looking for is located. Now this could be more complicated. I could say that maybe these boxes are in an elevator, and in that case, if they're not at rest, we would need to use second law to be able to tell us the difference between the normal force and the downward forces on this bottom box here. And this is kind of depends on what's going on. So let's try a different example with this in mind. So let's say I have a force that is pushing a box that is up against another box. So we'll say little m and big M. Actually, let's roll that back. Let's say this is 2m. Okay. And perhaps we know the acceleration of these two boxes. Since they're being pushed together, they should have the same acceleration. If I want to find the force between them, that's where I would break this. So M is being pushed on by F, being pushed back by the right box. It has gravity and a normal force. I'll say this is normal left. Alright, and then the 2M will have gravity, a stronger normal force. F is not acting on the far box, it's not acting on the right box, but the left one is. Now, if we know they're all accelerating at the same rate, then we should be able to set the mass times the acceleration equal to our net force in both cases. So we can see the force on the right box by the left is 2ma. And that will answer our question. However, I want to take a look at the net force on the left block. We know it's equal to ma, but I want to look at in terms of F that was applied to it. So the net force should be F minus the force of the right box, because it wants to resist that the change in motion. And we know that the force from the right should equal the force of the left on the right. So we can replace that with 2ma. I know that gets a little confusing, but here we can see F is going to be equal to 3ma, or we can say that ma is equal to F over 3. So it's almost like the left box here is, so this F here, is just 1/3 of it is getting applied to the first box, and 2/3 is getting applied to the second. So it's almost as if F is getting evenly distributed amongst these two blocks, even though that force is not physically touching the second block. And so that's one thing to keep in mind as well. And that all has to do with proportionality. The net force on the system has to be proportional to the mass. So that no matter how great F is, if it's 100 newtons or